Hi, Dr. Windish from all over the place these days, coming back to you with our educational series for anybody who's interested. Um, right before I closed my practice in Reno and moved to where I live now, and since I've been here, I've kind of been without inspiration for videos, and people had asked me, "Hey, when are you going to put up more videos?" And I said, "I don't know." Little did I know I was going to find inspiration in a unheard of virus that didn't exist at the time, that came from a town in a country or a town that I'd never heard of in a country on the other side of the planet. Was going to give me inspiration for a whole series of videos, but welcome back. Today we want to talk about nucleoside analogues, what they are, why you want one, and how you use them. And why? So let's back up to the local news. It is now May 2nd, 2020. Coronavirus continues to rage across the world. And at least here in the United States, Remdezavir received emergency FDA approval for use. So it's no longer compassionate use only. And you watch some of my older videos about what FDA approval means. This drug was never approved. So this is a big deal to now have approval for it. There is a lot of discussion about the research on Remdezavir. I'm not going to weigh in on it one way or another. Like it, love it, hate it. All three of the above. Think it's the greatest thing since sliced bread. Think it's spawn of Satan. I really not going to discuss that because my job's not to pontificate. My job here is to educate you about what these things are, how they work, why we use them. Fortunately, in my other life, before I went to medical school, I was a molecular biologist, and I was a pretty doggone good one. And I liked molecular biology. A lot of physicians major in biology because it's a natural fit for our pre-med curriculum and all the prerequisites we have to take for medical school. So it's kind of an easy major. And a lot of people don't actually like biology. They just major in it because that's what you do. And I once had somebody who was a bit of a mentor to me, who was a professor from another university, not the one I attended. I attended University of California at Irvine, and he was a professor from a university in Northern California, and he was a chemist. And he had heard rumors that I did pretty well in chemistry, and I did. I liked chemistry as well. And he said, well, hey, why don't you major in chemistry? And we had long discussions about, why you can major and what you can major in and the advantages of being a chemist versus a biologist. And at the end of the day, I stuck with molecular biology because at the end of the day, it was my first love. I also knew at that time I did not want to be a full-time laboratory investigator, and that I wanted to do clinical work and really wanted to do clinical work exclusively, which is what I do. But I love molecular biology. I always did. I still do. I still follow it to a certain extent, not like a researcher anymore, but like a very interested hobbyist, if you can have a hobby in molecular biology. So Remdezavir, and then before we get into the meat of this, let me just say, if you like my videos, please put a like and visit my sponsors who help me keep doing this. If you have suggestions or requests for future topics anywhere in the field of medicine, if I know about it, if I know anything about the topic, I will do a discussion of it for you. So please send me a note, put a note in the comments, something like that, and when I see it, I'll get it up for you. Do realize I don't know a lot about adult medicine. It's somewhat limited. I am a pediatrician and do pediatric and adolescent medicine with a lot of behavioral pediatrics and psychiatry involved. So those are kind of the things I know a lot about, and then molecular biology based off my background. So if I know about it and I understand it, I'll do a video for you. Anyway, so what is a nucleoside? What is a nucleoside analog? What is remdesivir? Well, remdesivir is a nucleoside analog, right? That is now a drug that has been FDA approved for use for treating novel coronavirus. Prior to that, it was used investigationally to treat a couple of cases of Ebola, and used in combination with a couple of other drugs that were either multiclonal, polyclonal, or monoclonal antibodies. So many people got remdesivir plus ZMapp or remdesivir plus some other stuff that were monoclonal antibodies. And for monoclonals, see my last video because that talks about those. And the effectiveness of remdesivir in Ebola, you can read for yourself. Ebola is a horrible disease with a very high fatality rate. It's extraordinarily contagious, and because it's so rapidly lethal, it's hard to assess the effectiveness of any medicine, because by the time you figure out somebody's got Ebola, they're so blasted sick that any chance of saving them is already markedly diminished. So it's a difficult statistical thing to prove. But it's a nucleoside analog. So what does that mean? And because you're going to be hearing a lot about this in the news over the next couple weeks, and maybe even the next couple months until a vaccine is found for coronavirus, thought we should talk about what nucleoside analogs are and what nucleosides are. So our genes are contained inside of DNA. Viruses' genes are either contained within DNA or RNA, and I have another video going back a little bit that talks about DNA and RNA and what the difference there is and why we have both. Viruses can be either one, either DNA or RNA. In the case of coronavirus, it's RNA. Honestly, with regards to Ebola virus, I don't have a clue. I don't remember. I want to say it's DNA, but don't quote me on that. Okay. DNA is made up of 4 components. So I can move my hands so you can see all 4 fingers. Okay, and these just repeat in sequences, long 100 million sequences. And the 4 components are adenine, thymine, cytosine, and guanine. Okay, and they pair up. Adenine always pairs, and DNA has 2 chains that run parallel to each other, and those chains twist as they go down. Let's see if I can do this in my small video camera here. In a helix, so they spiral downward, but they're always 2 parallel chains. Okay, adenine is always paired with thymine. Cytosine is always paired with guanine. And when you read DNA, when you actually use it to then make a protein, you only read 1 strand. Now, which strand you read varies from gene to gene, and we're not going to get into what direction you transcribe and stuff like that. But you might, for a given gene, for 1 million base pairs might go reading just the reading side. Adenine, cytosine, 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 adenine, adenine, thymine, adenine, guanine. Back in the old days when we ran sequencing gels to try to figure out the DNA sequence of a gene, you would take a photograph of the gel, and it'd be these giant photos. It was X-ray, used X-ray paper. So they'd be the size of a chest X-ray. So chest X-ray is huge. It's the size of my computer, bigger than my computer monitor. 2 of my computer monitors stacked together. And you'd send 2 people in a room, one guy with a ruler. You'd put the X-ray up on the X-ray box, and the guy with the ruler would put the ruler right across the gel, and you would label the 4 columns, and the gel would have 4 columns in it, and one would be adenine, thymine, cytosine, guanine, and you would just read down the list, and the other guy would sit there with a notepad, and he'd just write A, T, C, G, 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 T, C, C. Okay, and then when we had that, we knew the other strand was always the opposite base pair. So wherever there was an adenine, across from it was a thymine. Wherever there was a cytosine, across from it was a guanine, and so on and so forth. Okay. Synthetic nucleoside analogues are designed in a laboratory, and they can be inserted in place when in the process of replicating that DNA, they can be inserted in place of one of those base pairs or one of those bases. So one of the most famous nucleoside analogues ever to hit the market was something called, and I got to think of its name for a minute, Zytothymidine. So they took thymine, and that's actually the nucleotide. The nucleosides are, let's see if I can get this right, because it's been a little while since I've done molecular biology, and I know you guys are going to correct me, but it's thymidine, adenine, cytidine, and guanidine. And we're not going to get into what the difference is. It's kind of the precursor to the nucleotide. But the nucleoside, they then changed it just a little bit and put an azido group on there. And they put it at the point where the thymidine would connect to whatever the next base pair is. So you have kind of the nucleoside analogs are kind of these discs, and they have kind of a post that comes off of it. And then you attach a phosphorus to it, turning it into a from a nucleoside to a nucleotide, and then that phosphorus bridges to the next post, or bridges to the next disc, and there's a post coming off of that disc, and that's how you build the scaffolding. Well, in the azido group, when you put the azido group on there, when you go to bring the next disc in, it won't attach. And since it can't hook up, it falls off, the DNA is not replicated, and the cell dies. And that, in the case of azidothymidine, was a good thing, because the genome that you were trying to kill off was HIV, is HIV. Nucleoside analogs, and it worked moderately well. Now, the tricky part with nucleoside analogs is you want to develop one that will be incorporated into the genome of whatever it is you're trying to kill. In the case of azidothymidine, AZT, that was HIV. And there were a couple of other nucleoside analogs that people worked with, something called DDC, dideoxycytidine, and DDI, dideoxyinosine, which, if I remember DDI correctly, was used in lieu of guanidine. DDI and DDC tended to be pretty toxic, so we didn't use a lot of them, because the problem is nucleoside analogs are picked up by the synthetic mechanism for DNA in the body and for RNA in the body, and they're used by the human cells as well. So they wind up going both into the viral genome, DNA and RNA, and killing the virus. That's good. But they also go into the human DNA, RNA, and stop replication there, killing the cell. So you need to design a nucleoside analog that is preferentially picked up by the synthetic mechanisms of the virus and not picked up by the human synthetic DNA and RNA mechanisms. And that's the tricky part about designing a anti-metabolite like that, because it's just as toxic. If you're not careful, it has the potential to be just as toxic or even preferentially toxic to human cells as it does to the virus that you're trying to kill. Obviously, it can't be as toxic. If you're going to use it therapeutically, it can't be as toxic to human cells as it is to the virus that you're treating, because if it is, you'll kill the human long before you kill off the virus, which is why we didn't use a ton of DDI and DDC. And now in the modern world, we have some better meds that have come on the market for HIV that aren't nearly as toxic, and they're not nucleoside analogues. So AZT, I don't even know if you can still buy it. Nobody uses it in HIV therapy. It may still be used in laboratories because it's a really powerful research tool, and it's been well studied. We know what it does and what it doesn't do, and where it's taken up, where it's not taken up, what it does and doesn't kill. And since we understand it, we can use it for in vitro, test tube studies and interpret the results with a little more clarity. But therapeutically, it's not used anymore because it was taken up too much by the humans. Remdezavir, which is a nucleoside analog of a sort, is a different nucleoside analog, and quite honestly, I don't know exactly what it mimics, but it's one of those 4 nucleosides: adenosine, cytosine, thymidine, guanidine, and it mimics one of them and is preferentially taken up in viral DNA. From what I've read therapeutically in various prescribing manuals and stuff, it looks like it's not as toxic as AZT was back in the day for HIV. So that then means it's not picked up as much by human DNA, human RNA, as AZT was back in the day, because AZT had the potential to make you pretty sick. And Remdezavir doesn't seem to be doing that, so it looks like it's a little bit better tolerated. Nucleoside analog, Remdezavir is IV. AZT was ultimately orally. In the beginning, in the very, very beginning, it was IV only, because you have to be careful, because the GI tract is designed to digest the DNA of the animals we eat and break it down into pretty small groups. So they had some difficulty early on making it swallowable, but later they were able to figure out a way that you could actually swallow AZT, and they may ultimately do the same with Remdezavir. But right now it's IV only. So that's kind of what it does. So kind of as a recap, it's designed to be picked up preferentially by the virus in its genome reproductive mechanisms or machinery, inserted into the genome of the virus preferentially, but because it looks like part of the scaffolding for human DNA, the potential exists for it to go there too. And then interrupt the replication of the genome reproduction of the virus. If it gets picked up by the humans, it does the same thing and kills that cell. When you interrupt it in the virus, it kills the virus or prevents new copies of the virus from being made, and then your immune system will mop up. Now, the advantage here over AZT back in the day was, at least back in the day, in the early 90s, HIV has some rather unique properties to it, and HIV inserts so HIV is an RNA virus like coronavirus, but HIV is a retrovirus. So when it gets into the human cell, it reverse transcribes itself into DNA, which it then uses to replicate. Okay, coronavirus is not a retrovirus. It doesn't turn itself into DNA. It starts as RNA, it makes copies of RNA, and then it spins off, making viral particles that go out and infect new cells. HIV was unique, or rather unique. There's a couple of retroviruses where it gets into the cell, reverse transcribes itself into DNA, and AZT specifically was designed to target reverse transcriptase, which turned RNA into DNA, and try to block that step. Once it turned into DNA, this is where HIV is really insidious. It inserts its DNA into your DNA making it really hard to get rid of because now it becomes part of the victim cell's DNA. You can't just go in and carve it out. At least until about 10 years ago, you definitely could not go in and carve it out. Now there's something called CRISPR, and there's a lot of work with CRISPR to maybe be able to do that. And now we have some newer medicines that suppress the viral load to the point where maybe it stays gone and the immune system does recognize these funny cells and kill them off, and that seems to be the end of the problem. But going back into the 90s, so maybe there are some people, we're not 100% certain, but looked like there are some people who have actually been cured of HIV with some really aggressive modern therapy. But going back into the early 90s, these drugs didn't exist. We had AZT, and HIV made itself part of your DNA, and so it was with you forever. So when you got on AZT back in the early 90s or early 80s, because AZT was used for a long time, when you got on it, or I guess mid to late 80s, when you got on it, you were on it for a lifetime. And over the months is when it became more and more toxic, because the toxicities just build up as small amounts found its way into your DNA and disrupted those cells. But over the years, as that damage started to accumulate, you'd get sicker and sicker and sicker. The good news with coronavirus is it is not it's not a retrovirus. It doesn't do what we call intercalate itself or make itself permanently part of your DNA. So we're not talking about using it for 6 months, which, 6 months, 2 years, which back in the early 80s, on average from the time of diagnosis, the typical span from the time of diagnosis to fatality with HIV, and back in the early 80s it was 100% fatal, was about 6 months. That was in the early 80s. By the time AZT rolled around, it was somewhere between 6 months and 2 years for fatality. Coronavirus is not a retrovirus. It's not nearly as fatal as HIV was back in the day. And emphasis on back in the day for if you know anybody with HIV, I am not talking about modern therapies. This is not in any way supposed to frighten them. This is a historical side note, okay? But back in the day, this is where we were, and it was the dark ages. As somebody who treats HIV patients now and did HIV research in the late 80s, it's a very different world, and man, it's an exciting world. But we don't even use nucleoside analogues. But anyway, those people were on it for a long time, and the toxicities built up, and that was part of the problem. Here, this is not an issue. It's not going to intercalate into your DNA. Coronavirus won't do this. So you're only looking at being on it for a short period of time. How long do you need to be on it? I don't know the answer to that. Neither does anybody else. A couple of weeks, probably. Even with Ebola virus, how long did those patients need to be on it? Nobody knows. We're trying to figure it out. But we're not looking at 6 months, 12 months. We're looking at, 6 weeks or less, probably more like 10 days, 2 weeks, maybe 3 weeks, maybe 1 week. I don't know. And we have better ability to make synthetic stuff, synthetic bioanalogues now, based off of some other changes in industry. And so with that, it's not nearly as toxic, and you're not on it for as long of a time. So the goal here is not to make you terrified of it or make you think this is AZT. They are not the same, but they do operate by the same general mechanism, that they mimic a natural one of those discs that we use to build our own nucleotide or build our own DNA, RNA, but preferentially taken up by the virus, more preferentially with this drug than with AZT, and disrupt the viral replication system. So anyway, that's kind of what's happening. Stay tuned as the research progresses on Remdezavir. I'm trying to remember who I was listening to an interview with yesterday. I want to say it was Governor Cuomo, but it could have been any of a number of other people. When they asked, it was a male, is all I remember. But it was somebody. It was a senior administration from somebody in a state that was hit pretty hard with coronavirus. And they asked him what he thought about Remdezavir, and his exact words were, "We have to see." In fact, it must have been a researcher. Maybe it was somebody with the CDC. Anyway, he said, we'll have to see. We'd love for it to be a game changer. We are hoping it's going to turn out to be a game changer. But we don't know. And we don't know. So in the meantime, we're going to keep our fingers crossed that we found a game changer. And as people are looking at this, whether it turns out to be a game changer or not, you're going to hear a lot of talk about nucleoside analogues and remdesivir. So now you know what it does and how it works. Right now it has to be given IV. But like AZT, perhaps an oral version will come along soon enough. First, they got to make sure it actually works. And that it works sufficiently, and figure out how to dose it and when to dose it and all of that. Anyway, so as you hear more and more about this, and you will, now you know what it does and why you want to use it and why we're all so interested in it. In the meantime, stay safe out there. And again, if there's something you'd like to hear about, coronavirus related or not, feel free to send me a note. If you like the video, please like it. Please subscribe to my channel. Please visit my sponsors, because they're the ones that pay the bills. Do remember my videos are largely designed not to give opinions, but simply to give you the facts about what's happening. I do have a few over the years that have some opinions in there, and I'm always pretty clear about the fact that I'm going to get up on a soapbox today. Today, this video is not about soapboxing. This is about just how nucleoside analogues work and why everybody's so, and what this drug that everybody's so interested in, that's, number one on so many news stations right now, what it does. And I'll be back. Have a good afternoon.